Hello everyone. In this video we'll look into one of the quantitative techniques that's widely used and is a basis for many problem solving algorithms. That's basically the linear programming problem simplex. So in this video we are going to understand the simplex method in a more logical way rather than just being a step-by-step procedure. So stay tuned with me to get into the logics as well as the wonderful journey of the simplex algorithm. Now let's take up this problem or take up this particular method by a very practical question. Suppose in an industry or in a factory you've got two choices. You can produce product A as well as product B. And if I tell you that profit that I will earn on product A is rupees 3 and that on product B is, let's say, rupees 4. So which of the two products would you like to produce? Now if you say that the decision is product B, you are wrong, because I can produce both the products. So there's no constraint with regards to A and B, how many units of A I can produce, how many units of B I can produce. So definitely I'm going to produce the products to the fullest extent. So I'll produce both of them, I'll produce both A and B, and I will earn the maximum profit that is possible. So there is no problem, or there is no linear programming problem over here involved with regards to decision making. The problem comes when we are bound by the constraints. So it's a life lesson also, where we say problem is there only when and when there is some constraint, or there are some set of constraints which you face and you cannot fulfill it. Sir, I want to buy a Mercedes. Okay, it's a good dream, but sir, it's a problem for me. Why? Because sir, I don't have that much money. So that's a constraint for you, that you cannot buy a Mercedes. That's not a problem. Well, the problem arises because of the constraint. So similarly here, when there are no constraint, no problem at all, but the constraints arise and that gives rise to the problem. So let us go ahead with our first constraint. The first constraint that we have got is basically with regards to, let's say, raw material constraint. So product A, I'm talking about raw material requirement. Product A requires 4 kilograms of raw material. Product B requires, let's say, 2 kilograms of raw material. And if I say availability, how much raw material is available, so I say that 16 kgs of raw material are only available. Now this is something, a problematic thing, and that gives rise to some constraints, and that stops me from earning maximum profits or unlimited profits, because I've got only 16 kgs of material. So now if I ask you which of these two would you produce, A or B, just think for a bit. So now the way to think about it is, I'll say, okay, whenever I'm having any constraint, I will simply say profit per kg of raw material used. Profit per kg of raw material used. So basically that will become 3 by 4, because it's the 3 rupees and raw material requirement is 4 kgs, so that's 3 by 4. Then for product B, we say it is rupees 4 by 2. So definitely, sir, our choice is going to be this, because this is a larger number and I can get higher profits by producing B. So if I produce B, you can say entire 16 kgs when I am utilizing for producing B, per kg of B requires 2 kgs. Total I have 16 kgs. So I can produce 8 units of B, and those 8 units can be sold at a price of 4. So you can say 8 into 4, I can get 24 profit. On the other hand, over here, what I can get as a profit is when I produce only A, 16 by 4, so that will be 4 kgs or 4 units of A, and 4 units into 3, so we can say 4 into 3, that's just 12 rupee. So our obvious choice is to go for this one, right? Okay, so we solve this constraint, we solve this problem quite easily, because we said let's first find out what's the profit per unit of raw material or per unit of the constraint, and that gives us whichever product is giving me a higher number, that should be the choice for me. Now, but life is not so simple always. Suppose we have one more constraint. The next constraint is regarding labor. So we say, what is the labor requirement? So labor requirement is, let's say product A requires 2 hours of labor, whereas product B requires, let's say, 3 hours of labor, and total labor that is being available for producing these products are, let's say, 16 hours of labor are available. Now what should be our choice? What is the choice that we are going to have to decide which of these two products to be produced? Now I just want you to ignore this raw material constraint and just concentrate on the labor requirement constraint. So if I consider the labor requirement constraint, I get the profit per hour of labor. So if I ask my labor to produce A, that A is going to give me 3 rupees profit, and for that my laborers have to work for 2 hours. For earning a profit of 3 rupees, my laborers have to work for 2 hours. So definitely per unit of labor gives us rupees 1.5. Then coming back over here, 4 is the profit that I'm going to get by asking my labor to work for 3 hours. So per hour I'm able to get like rupees 1.33 or 4 by 3. So basically out of these two, we observe that when I am looking at only this constraint of labor hours, there I am observing that this is the preferred choice. So now here the problem comes, where both the constraints are giving me contradicting directions. Raw material constraint asks me to produce B, labor constraint asks me to produce A. That is where we have a need for linear programming problem, and obviously one of the methods to solve linear programming problem is simplex. So this is the background for how a simplex problem can be solved. So I just want you to memorize these numbers. Because we all are going to look at these numbers, and for our analysis purpose we're going to use these numbers. So profit of 3 and 4, raw material requirement is 4, 2 and 16 kgs available. Labor requirement is 2 hours, 3 hours and 16 hours available. So that is the case. There's a typical case. We are going to take it forward and we are going to understand the entire procedure of simplex method with this typical question. So to solve this, let's first convert this table, or so let's just convert this problem into a mathematical form so that we can take it forward to the simplex procedure and start solving it. So when I want to convert this into a mathematical form, here the mathematical formulation is going to have two parts. It's going to have two parts. The first part is about objective, and the second part is going to be constraints. Now since we are going to talk about over here profit, we're going to talk in terms of profits, my objective is definitely to maximize. So my objective will be to maximize something called as Z. Net Z is nothing but the total profit. Maximize Z. Now when I say maximize Z, I want to maximize my profit. So how much profit am I going to really make? So the answer depends on how many units of A and B you are going to produce. The answer totally depends on how many units of A and how many units of B are you going to produce. So let's make an assumption now. Let's simply make an assumption. We'll say let x1 and x2 units of A and B be produced. So we don't know as to how much exactly units of A and B is to be produced, because both the constraints are giving me contradicting results. So definitely we have to think that some units of A may be produced, some units of B may be produced. So let's assume them to be as x1 and x2. So the objective, maximize Z equal to, it's going to be my total profit. So here you need to understand that this Z is nothing but it is my total profit. So the total profit that I'm going to have, by producing 1 unit of A, I get rupees 3. By producing 1 unit of B, I get rupees 4. And a total profit that I'm going to get, it's like a combination of both. So for 1 unit of A, I'm getting 3 rupees. So if I'm going to produce x1 units of A, obviously my profit is 3x1 plus the profit from B. Profit from B is going to be 4x2. Then we have the constraints for this. So maximize Z, this was the objective function which we have set. Now there are constraints, and as we see, there are two constraints. One is with regards to the raw material, other is with regards to the labor. Now when I say it is with regards to the raw material, the constraint is with regards to the raw material, we can simply write the raw material constraint, being limited to 16 kgs. So I say with regards to raw material, the raw material availability is 16 kgs. So the maximum consumption that I can make is going to be less than or equal to 16. Maximum 16 I can do. So what's the constraint going to be? Let's have a look. We say 4 kgs of A is to be produced, 4 kgs of raw material is required for 1 unit of A, 2 kgs of raw material is required for 1 unit of B. So I'm going to produce x1 units of A. So for x1 units of A, the raw material that is required is 4x1, and for x2 units of B, the raw material that is required is 2x2. That's 2x2. Okay, then later on, after this constraints, let's go for the next part. This was the raw material constraint. Then the labor constraint is going to be based on these numbers. So for each unit of A, we require 2 hours of labor. For each unit of B, we require 3 hours of labor. So the total labor availability is only 16. So again the constraint is going to be less than or equal to 16. And then the constraints which I can place is 2x1 plus 3x2. And then this is what I call it as the labor constraint. Now looking at only this constraints, we are done with writing the constraints over here, but mathematically I need to bind this LPP. Because I cannot have the negative quantities of A and B. So my x1 and x2 cannot be negative. So if they cannot be x1 and if they cannot be negative, then I need to put that constraint also. So that constraint, we call it as non-negativity constraint. Where we say x1 should be greater than or equal to 0, and also x2 should be greater than or equal to 0. So both of them needs to be a non-negative thing, and therefore we place this constraint. Now this is the first part where we have converted our situation, converted our case study into a mathematical formulation which needs to be solved further to get the answer for x1 and x2. Now we'll look into the simplex procedure in which we convert these equations or inequations into simplex compatible format, So let's go ahead with the next part now, guys, where we're going to convert this into simplex compatible format and solve it further with the simplex steps. Let me just write this equations on the next slide so that we can work out on them. Okay, so here we have the question in front of us. This is the LPP problem that we just formulated. Now we have to convert this into a simplex compatible form. Now what is a simplex compatible form? The simplex compatible form is to simply remove these inequations without changing the meaning of the entire equation or the inequations. This should have the same meaning, and we just convert this into a simplex compatible form. Before that, just try to remember this was our raw material constraint and this was our labor constraint. Okay, so just these things are going to make the logics much clearer. So the simplex method is such that it doesn't accept the inequations. We need to convert these inequations to equations without changing the meaning of any of them. So for that purpose, we'll have to think it in a different way. Let me just write down the maximize z part, or just before that we leave some space to write something. So we have maximize z as 3x1 plus 4x2 subject to, talking about the first constraints now, the 4x1 plus 2x2. I want it to be equal to 16. I don't want it to be less than or greater than 16, because that is what the requirement of simplex is. Now definitely you cannot say that this constraint meaning and this constraint meaning is just one and the same, because over here if you go to the true meaning of this constraint stated 4x1 plus 2x2 should be less than or equal to 16. It means this particular portion that we have, this portion talked of raw material consumed, as to how much raw material is consumed, and we said that our raw material consumption should be less than or equal to 16. So 4x plus 2x2 should be less than or equal to 16. So we say that this particular portion is the raw material consumption, and the raw material consumption should be, we said, less than or equal to 16. And if I place a equal to sign, obviously the meaning changes, where we say that raw material consumption should be exactly 16. It may be exactly 16 or it may be even less than that. Right, so that is what our requirement is. So now how do I transform this? For that, I'll say, okay, let us keep this portion as it is. Let's keep this portion as it is. That is to say that this is our raw material consumption. So this is our raw material consumption. And obviously I cannot say that my raw material consumption should be equal to 16, because that's not the correct way to interpret this. So we say that raw material consumption is, I cannot say it is equal to 16, but definitely I can say that my raw material consumption plus raw material which is unused, or you can say idle raw material, both of them, the idle raw material, both of them should equal to 16. So I mean to say, some portion of your 16 units of raw material will be utilized or consumed. The remaining portion will remain as an idle or unused part, and that's the reason when I add both of them, raw material consumed and the unused raw material or idle raw material, both of them should add up to 16, and that idle raw material we are going to denote that by a set of variable as S1, which we call it as slack variable, So here I just write a line introducing slack variables S1, S2. Now we need to understand that this S1 and S2 are going to have some specific meaning, where I say S1 denotes idle raw material and S2 is going to denote idle labor. So that's idle raw material and idle labor. So that's the introduction of the slack variables, where we say S1 should be idle raw material and idle labor, and that S1 when we add it, this equation definitely makes sense, and we are in line with the original meaning, where we say raw material consumed plus raw material unused or idle raw material should be equal to 16. Now going by the same funda, we can even apply it for the labor constraint. The labor constraint, we say 2x1 plus 3x2 plus S2, and we know this S2 is simply the idle labor, and that should be equal to 16, because the total availability of labor is 16. So as we have stated, that this portion indicates the labor consumed or labor utilized, whereas the remaining portion S1 and S2, that indicates the idle raw material and idle labor. Now still our table is not yet complete. The equations are not yet complete to be fitted into the simplex table. These S1 and S2 needs to be assigned with some sort of constraints, or some sort of coefficients, because those are going to be definitely a part of my objective function. Now how much profit am I going to get by keeping my raw material idle? Of course nothing. If my raw material remains idle, I don't make any profit, nor do I lose anything. So we say plus 0 S1 because we don't get any profit, plus 0 S2 again because we don't get any profit on the labor expenses or on the labor hours. So when I'm keeping the resources idle, I'm not going to gain or lose anything unless and until there is some opportunity cost, or I'm going to pay something extra like that. But definitely that's the 0 S1, 0 S2, that's the no profit or no cost is being involved in it, and therefore we assign the values 0 over here. So the basic way of converting the simplex problem or LPP problem into a simplex compatible is to remove these signs. Now we have seen how do we remove the less than sign. We can remove the less than sign by introducing something called as slack variables, and those slack variables are simply added, and the inequations become equations. Now what do we do when we have a greater than sign? Well, we need to wait for it till we reach to the next question, where we will solve a maximization or a question where we have such type of things. Okay, so this way we have converted this into a simplex compatible problem. Now we will take it forward for solving it into the table, and even in the table we are going to understand the logic of all the numbers that we are going to write. So let me just take down this particular question on the next slide, and then in that same slide we can just start forming the simplex table. So here we go with the simplex questions available for us. Let's go for the simplex table Let me first write down the simplex table column headings. Remember, this is a typical format which I use. We may have some different format also, but the meaning remains the same. So let me just write down it. So we are going to have columns as fixed ratio, program, profit, quantity, x1, x2, s1, s2, and final column is called as replacement ratio. So this is the typical simplex table columns that we have got: fixed ratio, program, profit, quantity, x1, x2, s1, s2, that is the variables that we have, and then final column is the replacement ratio. In some of the textbooks you may find a different format also, where they actually call both these columns together, as basis, where they write both of them together as basis. So they don't write it as program and profit, they simply call it as basis, and they do write both the columns fully. Okay, so they call both of them as basis, and even they say quantity. Even for the quantity, they use just the variable as bi. So just don't get away with it, just don't think as to what these new variables are. You may find these numbers, so that when they say basis, just make sure to understand that it is nothing but the program and profit column, and where you see the bi, that's the quantity column, whereas the replacement ratio, that's just the same thing, or they may even sometimes call it as some term, what we do, bi divided by some number. So this is the typical format of a simplex table. Let's try to fill it up with our numbers. First of all, the simplex says we have to start with s1 and s2 as our initial stage, where I'm saying that currently what is your production. So obviously my production is nothing. Currently, before we are going to decide what is to be produced, my production is nothing, right? So currently my production is nothing, nil. So can I say I'm producing x1 and x2 units? 0 units. I'm not producing any units of them. So both of them are having 0 units. So basically what am I doing is, currently my resources are idle. And what was the variable that was indicating the idle resource? You're absolutely right. It's the s1 and s2. So I say in my program variable we'll have s1 and s2, s1 and s2, where we say s1 is the idle raw material, s2 is the idle labor. Now how many units of s1 and how many units of s2 are really idle? So at the initial stage, where we haven't produced anything, obviously the entire resource is idle. So I can say 16 units of raw material and 16 units of labor are fully idle. So in the quantity column I'm going to write 16. In the quantity column I'm going to write the number 16. Then talking about the profit, s1 and s2, can you tell me what's the profit that I'm earning right now? What's the profit that I'm earning right now from s1 and s2? Well, the profit that I'm earning is 0, because idle resources doesn't give you any profit. So definitely in the profit column we write it as 0 and 0. So that's what this part of the table talks of. This part of the table talks of as to what is your position right now, which units are you producing, or what is the status. So we say at the initial stage we are not producing anything. So s1 and s2, we have all the 16 units idle, and the profit on them is 0 units. Then coming to this portion of the table, this portion simply talks about how many units of the S1 and S2, or I can say how many units of program variables need to be given up. How many units of program variables need to be given up so that I can have X1, X2 produced. So if I ask you, tell me how many units of raw material or S1 I need to give up or I need to sacrifice, to produce 1 unit of X1. How many units of raw material I need to sacrifice to produce 1 unit of X1? So we say, refer back to this, sir. We have stated over here while drawing this equation that each unit of A, product A, requires 4 kgs of raw material. So can I say I need to sacrifice 4 kgs of raw material to get 1 unit of X1 or A? So here we say I need to sacrifice 4 units of raw material for X1, 2 units of raw material for X2, same way for S2, that is for labor. I need to sacrifice 2 units of labor to produce 1 unit of X1, and I need to sacrifice 3 units of labor to produce 1 unit of X2. Okay, then coming to these sacrifice ratios, how many units of S1 should I give up to get 1 unit of S1? Obviously, sir, it's a simple thing, it's just 1. To get 1 unit of S1, I need to sacrifice 1 unit of S1. Now understand this simple logic. For example, you have 2 godowns as X and Y, and you want to have the product in your godown Y from X. So how many units from X you need to move to get 1 unit in your godown Y? Of course, I need to move, or I need to sacrifice 1 unit from X to get 1 unit of Y, because it's the same product. So same funda over here, where we say that I need to sacrifice 1 unit of S1 to get 1 unit of S1. Same way even for S2. Now talking about S1 to S2, how many units of S1 should I sacrifice? Sir, how many units of raw material should I give up to get 1 unit of raw labor? Well, there is no such relation. Whatever amount of raw material you give up, that is not going to give you any labor hours. So basically we say these are the numbers which are going to be 0. Now to talk it in simple terms, we can simply write this portion. From our constraints. We can simply write this portion from our constraints, where we say these are nothing but the coefficients of the constraints. So we have x1 4, 2x2, s1 1. We don't have s2 over here, therefore we have 0 over here. Same way for the second line items. After that, we'll go for the next thing in the simplex stage, where we're going to say, or we're going to make a decision as to what needs to be produced. Now to decide what needs to be produced, next part that we say over here is the decision that I have to make, which product to be produced. So for that, let me simply write here Cj. Well, this Cj is nothing but the profit that we make per unit of these products. Now, what is the profit that I make per unit of x1? Well, profit per unit is that we have stated in our case study and also in the table. Over here in equation we have this 3, and x2 we have a profit of 4, s1 and s2 are having a profit of 0. Then the next thing that we calculate is Zj. Well, the Zj is indicating how much am I going to be having a opportunity cost if I produce x1. Now tell me, at this stage, when we aren't producing anything, are we really having any opportunity cost? Do I need to stop production of something else and produce X1, X2? Of course no, because anyways my resources are idle. 16 units of labor and 16 units of raw material are idle, and I'm going to utilize that because that's anyways a something which is idle and I don't have any opportunity cost for that. So definitely that Zj is simply going to be 0 in the first table only, but as and when we proceed with the second, third, fourth and fifth table, then Zj is going to have some value. Now over here, how do we get this Zj, by the way? Well, simply talking of this number 4, what was this number 4 indicating by the way guys? This number was, I need to sacrifice 4 units of S1. I need to sacrifice 4 units of S1 to get 1 unit of X1. I need to sacrifice 4 units of S1 to get 1 unit of X1. And okay, if I sacrifice S1, was I earning any profit on S1 that I will lose? So 0. So basically I'm losing out 0 into 4 with regards to S1 and 0 into 2 with regards to S2. But since both of them were idle, they didn't have any opportunity cost, we say Zj is 0. So that's basically 0 into 4 plus 0 into 2. So we have S1 as 0 into 4 plus 0 into 2 as the Zj value. Okay. Similarly for this, we have 0 into 2 plus 0 into 3. For this value, we have 0 into 1 plus 0 into 0. Okay. So that's about Cj and Zj. Then let's go ahead with the next thing, which is going to be the deciding factor for us, Cj minus Zj. So basically over here, when I produce X1, I'm going to earn 3 rupee and I'm having an opportunity cost of 0 rupee. So the net benefit for me is 3. Similarly for X2, I'm earning 4 rupee and there's an opportunity cost of 0 for me. So the net benefit for me is 4, and for the others also it is 0. So basically Cj was our gross profit, or I can say this was our gross benefit. This was our gross benefit. Zj was simply talking of opportunity cost, and this is the net benefit. This is the net benefit. Now talking of this S1 and S2, you observe that the net benefit in S1 and S2 is 0. That is currently now, sir, if you want to keep any of the resources idle, regarding to this, you don't have any cost with regards to it, or you don't have any profit also with that. Okay, so now looking at Cj minus Zj, we say if I produce X1 unit, I get 3 rupee benefit. If I produce X2, I get 4 rupee benefit. Out of these two, what will be our choice if I want to choose any one, not multiple times? If I want to choose any one, the obvious choice for any rational person is going to be this number. So we select this one and we mark this as the key column. I repeat, we select this one and we mark this as the key column. So this is going to be the key column for us. So let me just shade it as the key column. So this particular column is going to be the key column. Fine. Next thing, so here our decision, when I reach this stage, my decision is to produce X2. My decision is to produce X2, and that too basically 4 benefit, the maximum benefit we have. Therefore we are selecting X2 as 2 and 3. So this column we have marked it as key column. Now the next thing that we want to know, it's okay that we want to produce X2 we want to produce X2, but sir, how many units of X2 is to be produced? How many units of X2 is to be produced? Definitely the units that are going to be produced needs to be decided, because otherwise it doesn't make sense to go ahead with the simplex. So coming to that part, how many units of X2 is to be produced, that is going to be helping out in the replacement ratio. So now if you look at this number 2 and 16, what was these numbers indicating? 16 was the total capacity of raw material available. 2 was the sacrifice ratio between S1 and X2. So if you want 1 unit of X2, you need to sacrifice 2 units of S1. So you need to use 2 units of raw material to produce 1 unit of X2. I repeat, you need to use 2 units of raw material to produce 1 unit of X2. So now when I have 16 units available with me, how many units of X2 at the maximum can I produce? So we say that 16 units are available and each unit requires 2 units of, or I can say 2 kgs of raw material. So obviously sir, maximum that we can produce is 16 by 2 or 8. So basically how did we get it? That's 16 divided by 2. That 16 divided by 2 gives you the replacement ratio. Understand it with logic, not by pure numbers or the steps, because if you understand it by steps, you'll tend to definitely forget it. Understand that 4 was deciding factor to produce X2. Now the question is, sir, how much units of X2 needs to be produced? That will be given to us by this replacement ratio. So how do we decide how many units are produced? For that you need to see what is the quantity of raw material available, and what's the sacrifice ratio. So that's basically 16 unit is available and 2 kgs needs to be used of S1. So maximum I can produce 8 if I want to consume fully the raw material. Then with regards to S2, I say that's 16 by 3, because if I want to produce X2 by fully utilizing my labor hours, that's going to be 16 by 3. So that's 16 by 3. So here we get 16 by 3 as 16 divided by 3 over here. So what's the formula for replacement ratio, by the way, guys? So the formula is simply the quantity divided by the key column. Now the question arises, sir, what was the purpose? As I told you, to calculate the purpose of calculating replacement ratio. The purpose of calculating this replacement ratio, it is simply to identify how many units of S1 and S2 needs to be produced. So for S1 we say if I want to fully consume raw material, I can produce 8 units of X2. If I want to fully consume my labor hours, I can produce 16 by 3 units. of X2. So what will be my natural choice for selecting the number? Shall I fully consume my raw material, or shall I fully consume my laborers? If you think that we should go for 8, that is fully consume our raw material, then if you produce, just think of it, if you produce 8 units of X2, obviously 8 units into 2 का sacrifice ratio, so you consume fully 16 units of your raw material. Whereas for labor, if you produce 8 units, how many labor hours are required? 8 into 3, you need 24. Well, the availability is only 16, so I cannot go for selecting 8 as my choice, because if I go for producing 8 units of X2, I don't have that much labor force. But definitely I do have 16 by 3 units of X2 के लिए raw material. So our natural choice that we are going to have, let me just tell you, from this from this portion we always select the maximum, or instead of maximum I call it to be selecting the best positive. And remember, this is for the maximization problem, we haven't yet touched upon the minimization problem. Okay, so this is the best positive needs to be selected, and here we need to select the lowest positive. Why positive, sir? You just said lowest. Well, it needs to be positive because you need to understand the meaning of replacement ratio, which says it is the deciding factor how many units of the selected column is going to be produced. So 8 and 16 by 3. So that's basically the smallest one we are going to select. So we select the smallest one, and that particular row is fully marked as key row. So this is marked as key row. Now think logically, guys, and tell me, suppose if I produce 16 by 3 units of x2, which of my resources will be fully consumed? Because as we decided, the lowest needs to be considered. Which of my resources is going to be fully consumed? You're right, the fully consumed resource is going to be S2 or the laborers. Well, in that situation I need to write over here that outgoing variable is going to be S2, that is my laborers. My labor hours is fully consumed. Labor hours are fully consumed. So when I say labor hours are fully consumed, so S2 should not be over here. S2 should be kicked out of the solution, and in fact in its place we are going to have another variable, because x2 ban raha hai abhi. Initially in this table we didn't have x2 because we were not producing anything, but then we produced x2, and when we produce x2, we produce x2 to so much extent that the labor is fully exhausted. So obviously in place of s2, x2 is going to take its position. Well, to talk it in the other sense, we can say the in thing is nothing but the key column, and the outgoing is simply the key row. Okay, now we have just few things left out in this simplex table before we go for the second table. In this simplex table we have something called as fixed ratio. We have something called as the fixed ratio. Well, let me just calculate this fixed ratio right now without its logic, but when we go for the second simplex table we will clear out our logic in that sense. So for fixed ratio, the calculation fixed ratio formula for calculating fixed ratio is simply your key column divided by intersection. So you can observe over here there's an intersection 3 over here, so key column is 3, it's 2 over here, 2 divided by 3, and this is simply 1. So this completes our simplex table 1, which tells us to produce x2, and that will give us a profit of 4 per unit of x2 produced by sacrificing fully the idle labor hour. Well, this is not our answer. The answer right now, we need to go for checking it again and again whether there is further profit possible. Like here we said initially we were in a position where we were not producing anything, our entire resources were idle, and then we saw that if I produce x1 or x2 I do have a profit making opportunity, and then I say wherever is the higher profit of making opportunity, let's go for it. So we said let's produce x2 by fully sacrificing s2, and then let's see the scenario what happens. Let's go for the next table, the second simplex table, which will help us to make us closer to the final solution. Well, going for the second simplex table. Now in the second simplex table, I'm going to just touch upon the steps. The logic for the second step, second table, we'll have it in the next video. The second simplex table is going to have the same column headings as we have over here. So let's go for the second simplex table, guys. As I told you, we are going to just look into the method for second simplex table, the logic behind the second simplex and the third simplex tables. We'll be doing it in the next video. So let me just write down the column headings. Let me just write down the shortcuts now. Fixed ratio, program, profit, quantity, x1, x2, s1, s2 and replacement ratio. Now to start with, let's look into the first simplex table that we did. We said the incoming is going to be x2 and outgoing is going to be s2. So in place of s2, x2 will be placed. So we'll have over here x2 and the top s1 is going to remain same. Then we need to write down the profit that we earn on each unit of x2. We know it was 4 and s1 profit was 0. Now coming to this part of the table, where what we do is this particular row, which is the second row, in the previous table it was the key row. So whenever in the previous table that particular row is the key row, we can get this values easily by simply dividing each of these numbers by the intersection one. So that's like 16 by 3, 2 divided by 3, 3 divided by 3, 0 divided by 3 and 1 divided by 3. So let's do it. We have quantities as 16 by 3, 2 by 3, 1, 0 and 1 by 3. Now for this particular row, which was earlier a non-key row, now to fill up that non-key row, we will have to do a working. Let me just do it in a better elaborated way, where I say we are going to do it in a working. So in that working, we are going to have something called as A minus B. So for S1 we are going to do a working. So for S1 we are going to do a working where we say it is A, B and then A minus B. Okay, now what is this A? A are simply the old values. A are simply the old values. Old values are over here. We are going to calculate the values for quantity x1, x2, s1, s2. So the old values for quantity for S1, these are 16, 4, 2, 1 and 0. So let's write it 16, 4, 2, 1 and 0. Then B is simply key row multiplied by fixed ratio. So that is key row multiplied by fixed ratio. So this is our key row and this is the fixed ratio for S1. For S1 the fixed ratio is 2 by 3. So basically it is going to be 2 by 3 multiplied by each one of these numbers in blue. So we'll have this as 16 into 2 by 3, that's 32 by 3. The next number for x1, that's going to be 2 by 3 multiplied by 2, 2 by 3 multiplied by 2, so that's basically 4 by 3. Then the next number is 2 by 3 multiplied by 3, which is 2. Then next is 2 by 3 multiplied by 0, that's 0. Then 2 by 3 multiplied by 1, that's 2 by 3. Then a minus b, so we need to subtract this 16 minus 32 by 3, so it involves a bit of arithmetic calculation, and make sure you keep the numbers in fraction only, don't convert it into decimals. So here we have this as 16 by 3, 4 minus 4 by 3, which will give you answer as 8 by 3. Then we have 0, 1 and minus 2 by 3. So these numbers, we are going to place this set of numbers a minus b as the values for S1. So let me write it down over here. So this is 16 by 3, 8 by 3, 0, 1, minus 2 by 3. Well, the remaining steps are just one and the same that we had earlier, Cj, Zj and Cj minus Zj. So let's write down Cj, Zj and then Cj minus Zj. So we have Cj as the net benefit or the gross benefit or the objective function values, which is 3, 4, 0 and 0. But right now we don't have Zj as 0, because as we see, if you want to produce x1, I need to sacrifice x2. Because why am I saying that if I need to produce x1 I need to sacrifice x2? Because all the labor resource is fully utilized at this stage. So if I want any labor hours to be available for producing x1, I need to sacrifice or I need to reduce some production of x2. So obviously for this we have a profit in this, that if I stop the production, if I reduce the production of x2, I'll be losing 4 per unit of x2. So here the Zj calculation is going to be 4 per unit and 2 by 3 needs to be sacrificed. Anyways, S1 is not having any profit, so I won't be having any sacrifice cost for it. So this is 4 into 2 by 3, which is 8 by 3. This is 4 into 1, it's 4, then it's 0 and 4 by 3. Then we take the net effect Cj minus Zj, which is 3 minus 8 by 3. 3 minus 8 by 3, that will give us 1 by 3. And we have 0, 0 minus 4 by 3. Now observe here that Cj minus Zj for S2, now it is minus 4 by 3. Now this minus 4 by 3 is also called as shadow price. It is also called as shadow price, where we say that if I want to produce S2 now, I mean when I want to say I want to produce S2, it means I want to keep some of my resources idle. But remember, if you want to keep your S2 idle, you need to reduce the production of X2. So currently when we are at this second stage or this second table, we simply say that if I want to produce S2, or I can say I want to keep some of my labor hours idle, I need to reduce the production of X2. And if the production of X2 reduces, obviously I'll be losing profit earned on it, and that is where this resource is now having a value. It is now having a shadow price or opportunity cost of 4 by 3. Now definitely we know out of these things, out of these numbers, it gives me the idea as to which product is to be produced. So obviously 1 by 3 is a good number. It's a positive or the best positive number, and that helps me decide that this is something which I need to produce. So x1 needs to be produced, and when I say x1 needs to be produced, this particular column needs to be marked as key column. Then the next thing that we do, as we already know, is to see how many units of x1 is to be produced. For that we calculate replacement ratio. And how do we calculate the replacement ratio? It was simply quantity divided by x1. So quantity divided by x1, so 16 by 3 divided by 8 by 3, that's 2. Then the other number is 8, and we know out of replacement ratio we select the lowest positive and we mark that as the key row. So this becomes our key row, and immediately उसके साथ साथ we write down what is the incoming variable and what is the outgoing variable. What is the incoming variable? What is the outgoing variable? As we know, incoming variable is always the x1 or the key column. So incoming is x1, outgoing is s1, because this is the key row. Accordingly, we'll also have to compute the fixed ratio. So the fixed ratio is simply, as we have seen, fixed ratio, this is the key column divided by the intersection. So for the first one it is going to be 0, 8 by 3 divided by 8 by 3. For the second one it is 2 by 3 divided by 8 by 3. So that's basically 1 by 4. So this is the simplex table where we say that there is further improvement possible, sir. There is further improvement possible because I can make 1 by 3 profit, 1 by 3 net benefit possible if I bring in x1. So let's go for now the third simplex table. Let's go for the third simplex table, which will be possibly the final simplex table for us. So that's fixed ratio. So let me just give the headings: fixed ratio, program, profit, quantity, x1, x2, s1, s2, and then replacement ratio. Okay, here also it's almost the similar thing that we did over here. Here we have decided in the second simplex table that s1 needs to be kicked out and in its place x1 should come. So we'll have x1 and x2, and we know profits are 3 and 4. Then we see that this is the key row in the previous table, and we know how do we fill it. How do we fill this row which was earlier a key row? We simply divide throughout by the intersection value. So that's going to be 16 by 3 divided by 8 by 3, which is 2. Then 8 by 3 divided by 8 by 3, 1. Then we have 0 divided by 8 by 3, 0. Then we have 1 divided by 8 by 3, which translates to 3 by 8. And final one, minus 2 by 3 divided by 8 by 3. Minus 2 by 3 divided by 8 by 3. So that's minus 1 by 4. Then for this row, we know we have to perform the working note of A minus B. So let's perform the working note for this. So we have this for x2 as A, B, and then A minus B. So A, we know these are, A is nothing but the old values. So when I say A old values, so old values are this. So we have 16 by 3, 8 by 3, 0, 1, minus 2 by 3. Then B is simply the key row into fixed ratio. So key row numbers. Okay, my bad, I think old values are a bit different. Old values of x2 are 16 by 3, 2 by 3, 1, 0 and 1 by 3. B is this 1 by 4 multiplied by the key row. So 1 by 4 into 16 by 3, 1 by 4 into 16 by 3, that will be 1 by 4, 4 gets cancelled, so we have 4 by 3. Then next is 1 by 3 multiplied by 1 by 4 multiplied by 8 by 3, so that's basically 2 by 3. Then 1 by 4 multiplied by 0, that's 0. Then we have 1 by 4 multiplied by 1, 1 by 4, and 1 by 4 multiplied by minus 2 by 3, 1 by 4 multiplied by minus 2 by 3, so that's minus 1 by 6. So if I subtract them, we get the values as 12 by 3, which is 4. This is 0, this is 1, minus 1 by 4, and this is half, that is 1 by 3 minus of minus 1 by 6, so that's half. Let's write down these values now. So for x2, the quantity we have over here 4, 0, 1, minus 1 by 4, 1 by 2. All these numbers we got it from here, a minus b. Then the next step is to get Cj, Zj, and then Cj minus Zj. So Cj values are like whatever we had earlier, that's the coefficients from the objective function. 3 rupees, 4 rupees, 0, 0, these are the profits. Zj, we know it is 3 into 1 plus 4 into 0, so that's 3. Next is 3 into 0 plus 4 into 1, that's 4. Then we have here 3 into 3 by 8 plus 4 into minus 1 by 4, so that's basically we get that as 1 by 8. And then last one is 3 into minus 1 by 4 and 4 into 1 by 2, so that's 5 by 4. And if I look at Cj minus Zj, the difference between them, we say 0, 0, that's minus 1 by 8, that's minus 5 by 4, and we know both these numbers are what we call as shadow prices. These are called as the shadow prices. Okay, so that's how we get this final table. Now from here obviously there is no possibility for me to select any number which is a best positive, because I can't find anything else to be profitable. If I try to keep S1, S2 idle, I am losing out because there's a negative Cj minus Zj. So the answer that we have got, the final answer, or what you say as the solution, is basically x1 should be produced 2 units, x2 is equal to 4 units. That is our final answer, where we say 2 units of x1 and 4 units of x2 needs to be produced, and the profit that we are going to get is 3 into 2 plus 4 into 4, because 3 rupees is the profit on x1, 4 rupees is the profit on x2. So the total profit that we have is 22. So with this we complete the entire simplex algorithm for a maximization problem. Definitely I haven't discussed the logic for second and third simplex table, which I'll do it in the subsequent videos, but as of now this is quite sufficient for you to recap the entire simplex procedure step by step. Logics and all we can discuss it in the next class or in the next video that I have. So see you in the next video. Bye bye and take care everyone.